Welcome to this course on Control and Logic Systems Laboratory. This course blends two important aspects of engineering practice: control systems and logic systems. Control systems ensure that machines, processes, and devices perform as intended, even under disturbances. Logic systems, on the other hand, focus on decision-making circuits, switching, and programmed control. Together, they form the foundation for automation, robotics, and modern industrial systems. The laboratory emphasis of this course means our focus will be not just on theory, but on the practical implementation and measurement of control and logic systems. We will divide this course into two modules. Module 1, Control Systems Laboratory Practices. Module 2, Logic Systems Laboratory Practices. Let's begin with Module 1. Module 1, Control Systems Laboratory Practices. 1.1 Introduction to Control Systems in the Laboratory. Control systems regulate the behavior of machines and processes by automatically adjusting input signals to achieve desired outputs. In the laboratory, we study both time domain and frequency domain responses, compensation techniques, and control performance with various devices. These experiments train us to link theoretical control system analysis with real-world implementation. 1.2 Time and frequency domain measurements. In the time domain, we examine how a system responds over time when subjected to test signals like step or impulse inputs. We measure key performance parameters such as rise time, settling time, overshoot, and steady-state error. In the frequency domain, we study how the system responds to sinusoidal inputs of different frequencies. Measurements include gain and phase shifts, which are essential for assessing stability and robustness. Together, time and frequency domain experiments help us fully characterize a control system's dynamic behavior. 1.3 Compensation techniques: gain, lag, and lead. Real control systems often require compensation to improve performance. Gain compensation adjusts the amplification of the signal, directly affecting speed and accuracy. Lag compensation is used to improve steady-state accuracy while sacrificing some speed. Lead compensation increases stability margins and speeds up system response. In the laboratory, these compensators are implemented in closed-loop servo systems. By adjusting their parameters, we can observe how system behavior changes in terms of speed, accuracy, and stability. 1.4 Closed-loop control of nonlinear systems. Not all systems behave linearly. Nonlinearities arise due to saturation, dead zones, backlash, or other physical limitations. In the lab, we apply closed-loop control to nonlinear systems to understand how performance differs from linear cases. This also introduces the describing function principle, which provides an approximate method of analyzing nonlinear systems. By applying this principle, we predict and then verify behaviors such as limit cycles. 1.5 Phase trajectories. To visualize nonlinear system dynamics, we use phase trajectories. These plots show how system states evolve in a coordinate space, revealing whether trajectories converge to equilibrium, diverge, or form cycles. In laboratory experiments, observing phase trajectories helps us understand system stability beyond conventional time or frequency plots. 1.6 Performance of controlled DC motors. A very common laboratory experiment involves speed control of DC motors. Proportional control adjusts motor input proportionally to the speed error. This improves responsiveness but may leave some steady-state error. Proportional plus integral control eliminates steady-state error by integrating past errors, though it may slow down transient response. In practice, students measure motor speed responses under both control methods and compare performance metrics such as steady-state accuracy, stability, and sensitivity to disturbances. 1.7 Servo motor control: analog, hybrid, and digital. Servo motors are widely used in automation for precise position and speed control. In the lab, we test three modes of servo motor control. Analog control uses continuous electrical signals. This method is intuitive but limited in flexibility. Hybrid control combines analog and digital components, offering balance between speed and programmability. Digital control uses microprocessors and discrete algorithms, allowing for complex strategies, programmability, and adaptive control. By verifying performance in these modes, students gain an appreciation for the evolution from analog to modern digital control. Module 1 Summary. In Module 1, we explored control systems laboratory practices. We examined time and frequency domain measurements, gain, lag, and lead compensation, nonlinear system behavior, describing functions, and phase trajectories. We also studied DC motor control and servo motor performance under analog, hybrid, and digital control.